Exploring the world of color, colorimeters and photometers. Have you ever wondered how scientists measure color? It's not as simple as looking at something and saying, "That's red." We use special instruments called colorimeters and photometers. These tools help us quantify color in a precise and objective way. A colorimeter is like a high-tech eye that sees color just like we do. It measures the intensity of light after it passes through a colored solution. Imagine shining a light through a glass of juice. The colorimeter tells us how much of that light makes it through. Photometers are similar but focus on the intensity of light itself. They're used to measure the brightness of stars, the absorbance of solutions, and much more. Both colorimeters and photometers are essential tools in fields like chemistry, biology, and astronomy. They help us understand the world around us, one color at a time. Think of these instruments as digital artists, capturing the nuances of color that our eyes might miss. From the vibrant hues of a sunset to the subtle shades of a chemical reaction, colorimeters and photometers unlock a spectrum of scientific insights. Unpacking sunlight, VIBGYOR and the visible spectrum. We all know that sunlight is white, but did you know that this white light is actually a mixture of different colors? Think of a prism splitting sunlight into a rainbow. Each color in the rainbow represents a different wavelength of light. We can remember these colors with the acronym VIBGYOR: violet, indigo, blue, green, yellow, orange, and red. This sequence represents the visible spectrum, the range of colors that our eyes can perceive. Each color in VIBGYOR corresponds to a specific wavelength of light. Violet has the shortest wavelength, while red has the longest. When all these colors are combined, they create the white light we see from the sun. Our eyes are incredibly sensitive to these wavelengths, allowing us to experience the beauty and diversity of the world in full color. Rainbows in the sky, how prisms separate light. Ever wondered how rainbows form? It's all thanks to tiny water droplets acting as prisms. When light enters a prism, it slows down and bends. This bending, called refraction, causes the different wavelengths of light to separate. Since each color has a slightly different wavelength, they bend at different angles. Red light bends the least, while violet light bends the most. This separation of colors creates the beautiful spectrum we see in a rainbow. The same principle applies to prisms. The shape of a prism causes light to bend twice, once when it enters and again when it exits. This double bending enhances the separation of colors, creating a more defined spectrum. Section 4. The allure of opposites. Understanding complementary colors. In the world of color, opposites attract. Complementary colors are pairs of colors that appear opposite to each other on a color wheel. When placed side by side, they create the strongest contrast and visual impact. Think of red and green, the classic Christmas colors. They are complementary colors because they lie directly across from each other on the color wheel. Similarly, blue and orange, as well as yellow and purple, are complementary pairs. When complementary colors are mixed, they neutralize each other, creating a grayish or brownish hue. Artists and designers use complementary colors to create vibrant contrasts, visual harmony, and even optical illusions. Section 5. Measuring color. Diving into colorimetry. Colorimetry is the science of measuring and quantifying color. It involves using instruments like colorimeters to analyze the intensity and characteristics of light absorbed or transmitted by a substance. Think of it as a way to translate our perception of color into numerical data. Colorimeters shine a beam of light through a sample and measure how much of that light passes through. By analyzing the pattern of light absorption, we can identify and quantify the components of the sample. This technique is widely used in various fields. In chemistry, it helps determine the concentration of solutions. In the food industry, it ensures products meet specific color standards. And in medicine, it aids in diagnosing diseases by analyzing the color of blood or urine samples. Section 6. The Beer-Lambert Law, unlocking the secrets of color and concentration. The Beer-Lambert Law is a fundamental principle in colorimetry. It states that the absorbance of light by a solution is directly proportional to the concentration of the absorbing substance and the path length of the light beam through the solution. In simpler terms, the more concentrated a solution is, the more light it will absorb. Similarly, the longer the light travels through the solution, the more light gets absorbed. This law allows us to calculate the concentration of a substance in a solution by measuring its absorbance. This principle is crucial for many applications, such as determining the amount of pollutants in water samples, analyzing the concentration of drugs in pharmaceutical preparations, and studying the kinetics of chemical reactions. Section 7. Colorimetry in action. From labs to hospitals. Colorimetry plays a vital role in numerous scientific and clinical applications. In research labs, it helps scientists study chemical reactions, analyze the composition of materials, and develop new technologies. In hospitals, colorimeters are used to analyze blood and urine samples, aiding in the diagnosis of various diseases. For example, they can measure the levels of glucose in the blood to monitor diabetes, or analyze the bilirubin levels to assess liver function. From ensuring the quality of our food to advancing medical diagnostics, colorimetry is an indispensable tool in our modern world. It allows us to see beyond the surface, unlocking a deeper understanding of the world around us, one color at a time.